Want to run a little review for exam 2. And I'm using the review document, and I've highlighted some that I think are representative of the things that you should know and might show up on an exam. And the numbering is in sequence for each chapter. So chapter 4 starts all over again. That's why I put a chapter 3 up there. All right. So I got 69 of them. I'm going to have to move pretty quick. Oh, before I do that, has anybody got any problems that we need to deal with first?
Are you going to do 27?
27. On chapter 3? Okay, let's see. Oh, I don't have that one. Okay, we can do that one first.
Okay.
All right, let's see what it says. You take an aspirin tablet composed of carbon, hydrogen, and oxygen only, with a mass of 1 gram. Burn it in air, collect 2.2 grams of carbon dioxide, 0.4 grams of water. The molar mass of aspirin is between 170 and 190. What's the molecular formula? Okay. This is a 2-step process. You find the empirical formula, and then you work your way to the molecular formula. But it's probably confusing how you get the carbon and the hydrogen and the oxygen out of those analyses. Is that your sticking point? Okay. Okay. So let's see. Let's put what we know up here. It's carbon, hydrogen, and oxygen. And we're given a 1 gram sample, 1 gram total mass, 1 gram sample. And we find that we get 2.2 grams of carbon dioxide. So let's do it this way. 2.2 grams there. And water vapor, we get 0.4 grams. So it's water, 0.4 grams. Okay, what we need to find out is how much of this gives us carbon. We can't do oxygen yet because we're burning it in air, right? There's excess oxygen. So this one has to be done by difference. And that's where we need this value. But first we have to find out how much carbon and how much hydrogen. So what you need is the mass percent of each one. And the mass percent of carbon and carbon dioxide is, actually the mass fraction would be more useful rather than mass percent. So what's the total mass of carbon dioxide? Let's see. 12.01 and 2 oxygens is 32. Right, so we have 1, 0, 4, 44.01. So the total mass is 44.01. How much of that is carbon? 12.01 grams carbon per gram of carbon dioxide. So this is grams of carbon dioxide. So this is a dimensional analysis problem. We want to cancel the carbon dioxides and leave us with carbon. Okay, so let's do that one right quick. We have 12.01 divided by the total, 44.01. Okay, that's 0.273 something times 2.2. And that means we have 0.60, and I'm going to keep more decimals than I should. 364 grams of carbon. The reason I do that is to eliminate rounding error. So we're going to multiply, 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 and we'll come back to 3 significant figures later. So this one would be what? Remember what the molar mass of water is? We did it several times in class. 18.02 grams of water. And this is water. So how much of that is hydrogen? Well, 1.01 is 1 hydrogen. 2.02 would be 2 hydrogens. grams of hydrogen. Okay, now this one is 18.02 on the bottom for the total. But on the top, we need 2. I did that one right, didn't I? Maybe I miscalculated. So I get 0.45. Let's do that. And now for the oxygen is that from this. So let's add these together and subtract them from 1. So this should be 0.35. That won't round off correctly, will it? Should be 1.0. Wait a minute. That's more than a gram, isn't it?
What'd you say you get for the hydrogen? The 0.45 there? Because I've got 0.045, that's what I got.
Oh, 0.45. Thank you. That'll work now. So did we get 0.355? That looks better. Okay. Now it'll probably work. Let's go ahead and leave this one. 0 hydrogen carbon. Squirrel these in here. 0.600. This is 0.045. This is 0.35. Okay. Now, 12.01 grams per mole. Yeah, 1.01 grams mole. And 16. Yeah. There we go. So I get, this is about a half. No, this is 0.05. Yeah, 0.05 moles. I'm gonna start rounding now. 0.045 divided by 1.01 is 0.046. And this is 0.355. 16. And this is 0.022. Okay. Now the smallest one is this one, correct? That's about 2. And this is 2, 3. No, I better not do that. 2.09. 0.05 divided by 0.022 is 2.27. So we get rid of that quarter by multiplying by 4. And 4 will give us about 9. And 4 here will give us about 8. And this would be 4. So we're saying that C9 H8O4. And the empirical weight for that is 9 times 12.01. And then 8.08 for the hydrogens. And then for 32, 64 for the oxygens. So the empirical weight is 180 grams per mole of this one. Right, so if we do that, and it's supposed to be between 170 and 190, which it is. So this is equal to 1. So we're saying that it's C9H8O4. Yeah, yeah. And that fits. Right, this is the structure. Let's count them up. That's a carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Hydrogens. There's one each for here. It's 1, 2. There's one here. One. There's two. One here. No, wait a minute. 2. No, there's no hydrogen there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Is that right? There should be one here, one here, one here, one here. Acetyl salicylic acid. Oxygens, 1, 2, 3. Well, it should be 4. Oh, there. No, 1, 2, 3. Where's the other oxygen? Oh, my mistake. This should be like that. So that's 4. 1, 2, 3, 4. 1, 2, 3. Wait a minute. That can't be. There you go. 1, 2, 3. Okay, now we got it. I drew it wrong. 1, 2, 3, 4 oxygens and 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. That's it. Okay, I'm happy. You understand it better now or worse?
A little better.
I'll tell you what. We shouldn't have to do any more problems with molecular formulas in it, so we can save some time there. We'll just skip over those. Let's go back to the first one and see if that's of the same nature. We won't do it. Oh, excuse me. One more. Here we go. No, this is different. So we'll go back to number 1. I think I need a new marker too. It lasts very long. Okay, naturally occurring copper exists in 2 isotopic forms, copper 63 and 65. The atomic mass of copper is 63.55 atomic mass units. That's the weighted average of copper in nature. What is the approximate natural abundance of copper 63? Now, since they didn't give you exact values for the copper 63 and copper 65, we know from what we've learned in this chapter, that those values are protons plus neutrons. They're not actual weights compared to the standard carbon-12. So we're stuck if we don't just use 63 and 65 whole numbers. for their values. We're forced to do that. So how would we calculate that 63.5? We would take 63 for one copper times its abundance, right? Which would be some X value. Yeah, that doesn't look right. Let's try this. That would be the first one. And this would be a value for the 63 abundance. And 65, is it? Yeah, 65 would be times what? Well, if X is the 63 abundance, yeah, natural abundance of 63, we want that to be X. Then this one would be 1 minus X, right? Because that's what's left over. Right? If we're going to use fractions, this is a fractional abundance of 63. So 1 minus that fraction would be what's left over. And that goes for the other one. Did I lose anybody there? It's like 100%. If 50% of it belongs to that value, then the other 50% belongs to this one. If X is a half, then 1 minus X is a half. Okay. So that gives us 63X and 65 times 1 minus X. And then the value that we get from that is 63.55. If you add them together, right? That's the weighted average that we performed. So if that's the case, then we can set up a plus 65 times 1 minus X and just solve for X. We're good so far? Or did I lose somebody?
How'd you get the 63.55? That's where I got lost.
Here? Oh, here. Oh, it came out of the problem.
Oh, okay.
Yeah, that's the atomic mass. That's the weighted average that we can read off the table, actually. So if we solve for X, that means this one, we have to distribute this one out as 65 minus 65X, 63X. So this is going to be minus 2X. This is a plus. This is equal to 65 is the whole number here. Combine these two is minus 2X, 63.55. So we bring this one over here as a negative, and that would be 65. B. That's a 5. 5, 4, 1, right? Negative. Because this one comes over as a positive, it's a negative now. So that makes this a negative 1.45 is equal to negative 2X. So the negatives cancel, and we say X equals 1.45 divided by 2. So that's about 0.73. Something like that. Okay, so that's the fractional abundance. Percentage, it would be 73. Okay. So there's no 73 there. Closest one is 70. So it's like I always say with multiple choice questions, unless you have an out like none of the above or something like that, if you only have those numbers to work with, pick the best one. And the best one is 70. Yeah, things are in the way, aren't they? Camera's getting it all, including all the mistakes. Okay, let's see what number 3 has to say. Oh, this is okay. I asked you this one in class. Let's see if you remember the answer. The average mass of a carbon atom is 12.011 atomic mass units. Assuming you were able to pick up only one carbon unit, that is a carbon atom, chances that you would randomly get one with a mass of 12.011 is 0%, right? It's a weighted average. You won't get Never, you will never, ever get that value from one atom. Not in the normal universe. Okay, 4. What's the mass of 4 atoms of copper in grams? This is a dimensional analysis problem. 4 atoms of copper. If we're trying to get to grams, we need a conversion that will put us in position to use molar mass. So we need to convert that to moles first. Atoms. What's the magic number? Starts with an A. Avogadro. Okay. Divide that into that, gives you moles. Now we can convert moles to grams. So we go to copper. We were just looking at that one with 6355. There you go. Work that problem out, and it should give us 4.22 times 10 to the minus 22 grams per atom. Excuse me, no, total that many grams, because we have 4 atoms. My mistake. So each atom would be about 1 times 10 to the minus 22 grams. All right. 6. So you have a sample of zinc, aluminum, zinc and aluminum, equal number of atoms of each. Which of the following statements concerning the masses of the samples is true? All right, let's look at zinc and aluminum. What are their molar masses? Zinc is 6538. This is atomic mass units per atom on average. Aluminum is 2698. Units per atom. And we have the same number of atoms? Yeah, equal numbers of atoms. Okay. If we have equal numbers of atoms, just pick it. It doesn't matter. The mass of zinc would be about 2.5 times the mass of aluminum, wouldn't it? If you have the same number of atoms. Okay, see which one of these statements met. The mass of zinc sample is more than twice as great as the mass of the aluminum. Yeah, that fits. Right. And do we have any squirrely ones down there? No, they're unique answers. They're none of those, 2 of the above, none of the above, all of the above, that kind of thing. So if they're unique answers, you can just stop when you find the right one. And A is a good answer. But before we went looking for the answer, we learned what we actually have in hand. How about 7? Sample of ammonia has a mass of 43.5 grams. How many molecules are in this sample? Okay, this is another dimensional analysis problem. 5 grams of ammonia. Right. We haven't talked about the formula for ammonia. So if you get to a problem like this and it doesn't give you a formula that you need to work from, just ask me and I'll tell you. That's ammonia. 1 nitrogen, 3 hydrogens. But we want to turn that into molecules of ammonia. So first of all, we've got to convert grams to moles. Right? So what's the molar mass? Nitrogen is 14.01 grams per mole, and then 3 times 1.01. So it should be 17.04. That gets rid of the grams and leaves us with moles. Now we can convert moles to molecules. Same as before, Avogadro's number. And that should give us 1.54 or 24. Molecule of ammonia. Now, does that make sense? Let's see, this will be like 2.5 divided into that. Three. Yeah, close enough. All right, how about 8? Moles of hydrogen sulfide are contained in 49. This is, I think I told the class at the very beginning, dimensional analysis can be used to solve a lot of chemical problems. 49.7 grams of hydrogen sulfide. Oh, okay. Here's the fly in the ointment. 49.7 grams. Hydrogen sulfide. How do we write hydrogen sulfide? And we know it's got hydrogen in it. We know it's got sulfur in it. So how do we balance that? Well, sulfur is a chalcogen. It's usually -2. When hydrogen's first in the formula, it's a +1. So we need 2 of these. Okay. H2S. Now we can work, it looks like a 5. Now we can work the problem. Grams per mole first. And it only asks for moles. So all we have to do is find out what's the molar mass here. 2.02 for the hydrogens, and the sulfur is 3207. 32.07. So that's 34.09. That gets rid of the grams, leaves us with moles. And if we did the calculation right, it should be like 1.5, maybe something like that. Yeah, 1.46. Okay, so the trick to this one is figuring this out right here. All right, let's see. For which compound does 0.256 mole weigh 12.8 grams? All right. So the way I would approach this, since you have formulas for each of the compounds, you can calculate their molar masses. So let's calculate the molar mass of the compound and then compare it to the others. Grams per mole, 12.8 grams per 256 mole. So the molar mass of the compound is going to be 12.8, 0.256, about 50. In fact, exactly 50 grams per mole. All right, we should be able to get through these quickly by estimating. Do we have an E? E is none of these. All right, C2H4O, C2H4O, CO2, CH3Cl, CH3Cl, and C2H6. Okay. Let's see if we can estimate these and get close. This will be 24 plus 4 is 28 plus 16 is 44. So that's too small. Right? That's too small. Carbon dioxide, that's like 12 plus 32 is 44. That's too small. Right? See what I'm doing? Okay, let's see. 12 plus 3 plus 35, 45. Or 35.5. So this will be 580. Let's see. Hold on. That was pretty close. This is a good candidate right here. How about this one? That's 24 for carbon, 6, so that's 40. So by process of elimination, well, since none of these, then we do have to finish calculating this one because it's the most likely candidate. 12.01, 3.03, and 35.45 for the chlorine. So we just add those together real quick. $49.49. Is that right? Yeah, 49. And 8. 50.49. All right. Here's the problem. I would expect an answer of C as the closest. But since we've got none of these, and this is not exactly what we calculated, then you could put none of these and you'd be right. Right. So if something like this shows up, this is an example. If something like this shows up on a test and you show me your calculations, say, that's a correct answer. I'll give you credit for it. But my key may tell me to mark it wrong because it's not C. But all you have to do is just show me your work and you got the money. That is, if I don't catch it while I'm making up the exam and fix it, because I can anticipate the problem. Molar mass of barium sulfite. Yeah. This is where you have to know how to write the compound. Right? You have to know that barium is Ba and recognize sulfite as a polyatomic ion. So you got that list of polyatomics, which will be on the exam. There'll be a page of them there. The sulfite is SO3. Barium is an alkaline earth. It's a 2+ charge. Sulfite has a 2- charge. So that's it, just 1 and 1. Then you add up the barium at 137.33 and sulfur at 32.07. And 3 times 16 is what? 48. And add those together. 15, 217.40. Yep, E. This is grams per mole. Sometimes I just, out of habit, leave the units out. If I'm going to use it in a calculation, I have to know that that's right. All right. That was 11. What's the mass of 6.761 moles of sodium hydroxide? All right, we'll set this up real quick. Sodium hydroxide. Hydroxide is a polyatomic ion with a -1 charge +1, so that's sodium hydroxide. And we want to convert 6.761 moles to grams. So we need the molar mass, right? Moles on the bottom, grams on the top. So sodium is 23. Oxygen 16, hydrogen is 1.01. That's it's 40. 40.01, right? So 40 times 6 is about, well, and 3/4. So 10, let's see. 6 times 4, 40 is 240, and then 3/4 is 250. 270.4? Yeah, I better do the calculation then. Just in case I made a mistake. I was trying to estimate. 270.51. 0.4. There must be a rounding error in there somewhere, but that's the best answer out of that group. All right. What about this one? One molecule of a compound weighs 2.93 times 10 to the minus 2. The molar mass of this compound is. Oh, okay. Dimensional analysis. We are given 2.93 times 10 to the minus 22. Grams per molecule. Per molecule. And if we're looking for molar mass, what units do we need? Grams per mole, right? Okay. So we want to cancel molecules and leave us with moles. Magic number. That'll leave us with grams per mole. And we should end up with the 176 grams per mole. Let's see if I make this one a little more negative. I don't know if that's going to work. Minus 22. Better do that one. 2.93 exponent minus 22 is 6.2. Yeah, 176. That's D. I wasn't estimating too well up here. All right. Oh, this is a fun one. 17. We're still in chapter 3. I'm going to run out of time. It's because I wasted so much time on 27. A compound is composed of element X and hydrogen. So it's got X and hydrogen so far. Analysis shows the compound to be 80% X by mass. So it's 80% X mass. Okay. 3 times as many hydrogen atoms as X. Well, this is 3. Okay. Which element is element X? All right. Okay. If we have 100 grams of this sample of that material, there will be 80 grams of X and 20 grams of hydrogen, correct? Okay. We can calculate the number of moles here. Let's do hydrogen first. So this is grams per mole in that formula. 20 divided by 1.01. Is 19.8 moles of hydrogen. Well, if there's 3 times as many moles of hydrogen as X, then X is going to be a third of that, isn't it? The ratio is 3 to 1. Or we could do it this way. We could say moles of hydrogen to moles of X is 3, and 1. So we just divide 3 into 19.8, and that tells us how many moles. Let's see, 6.6. So that's 6.6 moles of X. Right? So we know how many grams of X we have because we started with 100 and 80 grams of it is X. And that number of grams is represented, is associated with 6.6 moles of X. So we can calculate grams per mole. Grams per 6.6 moles. So what does that give us? 12.12 grams per mole. All right. So we're going to find out that element. We don't have the number of protons. We don't have the atomic number, but we do have the molar mass. So we just go to our chart and we follow along until we get something close to 12. It looks like carbon. And the reason it's not 12.01 is experimental error. Okay. All right. Let's see, 18. Which compound contains the highest percent of mass of hydrogen? Okay, this is Henry Ford time. Right? So HCl, water and sulfuric acid. And the last two, H2S and HF. And we're looking for percent by mass of hydrogen. So calculate the percent by mass, we just need molar mass of the compound and the mass of hydrogen on top. Right? Two of them, 2, and 1. That's how many grams of hydrogen per unit mole. So the total here is 3545 and 1.01. I should be able to do that in my head. That's 3646 grams. That's the total mass of this unit times 100. Since I've already got them in my calculator, I'm going to go ahead and convert, divide. That's 27.7% nitrogen by mass, mass percent. Okay, how about this one? Well, we know what this one is, 18.02. Times 100. This is 11.2% hydrogen. That look right. 1.01, 36.46. No, I thought that looked strange. Got my decimal in the wrong place. 2.77. There we go. This one is 2.02 for the hydrogens, 3207 for the sulfur, and 64 for the oxygens. 9809. 98.09. And 2.02. And that's 2.06%. And then this one is 2.02 for the hydrogens and 32.07 for the sulfur. Divide that into 2.02 is, let's see, 32.7. Forgot to write it down. 34.9. Five point nine. 5.93%. And this one, fluorine is 19, I believe. Yeah, 19. So 19 plus 1 is 20.01. 1.01 and 20.01. And I get 5.05. Now, do I need to check this one again? Maybe I better. That's right, 11.2. So, water is the highest percent hydrogen. Right, let's see. Oh, a substance contains nitrogen, hydrogen, oxygen. How many grams of hydrogen there in 153 gram sample of this substance? All right, how would we approach this one? We're given mass content of the sample. We can calculate the percent by mass, correct? So if we know the percent of hydrogen from that previous analysis, then we can use that value against the sample that we actually have, right? So what's the total? We want percent hydrogen, 5.05. And then the total is 5.05 plus 35 plus 60. And I would say just keep it a fraction because we're going to multiply a fraction times 153 anyway. Or you could do the whole thing like this. Now to give you the answer in one calculation. 5.05 and then 35 and 60. That's so it's actually fraction is 0.0504, 0.0505. This is 0.0505 fraction times 153, which is 7.7. Right? 7.2. Okay. Moving on. Let's see. Each molecule of testosterone contains 19 atoms of carbon. The mass percent of carbon is 79.12. What's the molar mass of testosterone? All right. I guess we ought to do this one. Again, this is dimensional analysis. So where's our starting point? 19 atoms carbon per molecule. And where we want to end up is molar mass. Grams per mole of testosterone. That's grams of testosterone per mole of testosterone. This is 19 atoms of carbon in the molecule. We're also told that the mass percent of carbon is 79.12%. So what if we say 19 atoms of carbon weighs what? Yeah. I tell you what, let's take another approach. If we have 19 atoms of carbon, how many moles is that? Let's see. Grams. Let's do grams because we're given mass percent. 79.12 mass percent. So let's find out what's the mass of this carbon. Atoms. And this is moles. Then we can convert moles to mass. With this ratio. That'll tell us how much mass of carbon is there. So 19, 6.0223 divide, and then 12.01 times. So this is okay. This is 3.789 times 10 to the minus 22 grams per molecule. Right? All right. So if that's the grams of carbon per molecule, what's the grams of testosterone per molecule? This represents 79.12%. 79.12% of the mass of one molecule. So we could look at it this way: 79.12 grams of carbon, per 100 grams of testosterone. Okay. So if we start over there, then this has got to be on the bottom to cancel that. Here's what I'm saying. Let me just continue over here. Where I'm headed is to get rid of the grams of carbon and leave us with grams of testosterone. So that's 79.12 per 100. Right? That many grams of carbon per 100 grams of testosterone. And that'll tell me the grams per molecule of testosterone. Right? Because we still got this one. We're going to cancel that one and go back to this one. 100 times and then 79.12. Right. Am I following along what I did before, or am I making it harder? So what I end up with is 4.789 times 10 to the minus 22 grams of testosterone per molecule. Right? Okay, if that's grams per molecule, and we've got 6.022 times 10 to the 23rd molecules per mole, guess what that does? Cancels the molecules. Now we have grams per mole.
I think you did it harder just now than what you did right now.
I am not surprised at that one bit. So I get 288.4 grams per mole. Yeah, E. I probably set it up with one step.
You pretty much did.
22. 19 and. Oh, I took a different, approach. Yeah, I sure did. Mhm. It's nice to know that you can work the problem more than one way. It's just that that's more efficient. Let's see, I haven't got any that I can skip yet. An oxide of iron has formula Fe3O4. What mass percent of iron? You guys can do that, right? Well, I'll set it up for you. How about that? 24. If this is the formula, Fe3O4, by the way, there's no such molecule. How do I know? Because oxygen should be -2. That means this would be -8. So how do you get -8 divided by 3? You can't have a whole charge, right? Okay, so here's what it is in reality. It's Fe2O3 and FeO. There's 4 oxygens, there's 3 irons. So this one works out to -2, and this is +3. And this one is -2, and this is +2. So it's a mixture of +3 and +2 valence irons. But for calculation purposes, this works okay. Fe3O4. All right, what's the mass percent of iron? Okay, so we need 3 times what iron is. 5585. 5585 divided by 3 times 5585. Right? It has to be in both numerator and denominator. Then add the oxygen in there, which is 64 times 100. And that should be 72%. Okay. All right. And 4.26. Ammonium chromate contains what percent nitrogen by mass? You guys can do that, right? The trick is to realize that you have 2 nitrogens, not just one, because it's inside the parentheses. I don't have to do it, do I? Okay. And let's see, 27 we skipped already. Let's see. A hydrocarbon is found 85.6% carbon by mass. What's the empirical formula? If it's carbon and hydrogen and it's 85.6% carbon, and it's only got hydrogen left over, what would that be? It'd be 100 minus that, wouldn't it? Like 14.4%. Yeah. And then you just proceed. We have to convert this to mass before you can determine the empirical formula. That's all it asks for, empirical formula. So we would say, assume 100 grams sample. Now you've got 85.6 grams and 14.4 grams of each. I might as well go. So this one needs to be converted by dividing 12.01. This one is 1.01. Oh. Okay. This is 14.3 and 85.6, 12.01. And this is 7.12. 7.12. Divide by the smallest one. And this is 1, and this is about 2. So it'd be CH2. Okay. All right, 32. Empirical formula of styrene. Okay, this one's pretty quick. The empirical formula of styrene is CH. So we need a multiplier there to find out what the molecular formula is. Right? The empirical weight of that formula is 12.01 plus 1.01, which is 1302. So we need 13.02 times some value N to give us 104.1, because that's the molecular weight. So you should divide 13.02 into 104 to find out what the multiplier is. And it's pretty close to 8. So C8H8 would be the best answer. Adipic acid. All right. You guys can do that one. Right. You just, if you're given percent by mass, just assume 100 grams, and then the values become grams. Then you work it from there. Vitamin C. The only thing left out here is oxygen. If we know it's carbon, hydrogen, oxygen only, then 40.9 plus 4.58 subtracted from 100 gives you oxygen. Now you've got all three values and you can work it from there. Right? Gotta go. Oh, sorry. No, that's my problem. Just long-winded. We're not even chapter 4 yet. So if you have to go, I can stick around today. I don't have to be gone. So, but if you have to go, then you can watch the recording. How many of the following are true concerning balanced chemical equations? Well, let's see. The number of molecules is conserved. That's talking about coefficients. No, add up the coefficients on one side, they can be different than the other side. So 1's not true. 2, the coefficients for reactants tell you how much of each reactant you are given. That's a little misleading. How much is mass, right? They don't tell you that. They tell you how many molecules. Atoms are neither created nor destroyed. That's a good one. Number 3. 4, the coefficients indicate the mass ratios. No, that's another way of saying 2, and it's wrong. 5, the sum of coefficients on the reactant side, that's another way of saying 1, and it's wrong. So there's only one of them that's correct out of that whole bunch. In balancing an equation, we change the blank to make the number of atoms on each side of the equation balance. Can't change the formulas, right? Can't mess with the subscripts, coefficients. That's the only way you can balance an equation. Uh, 39. What's the coefficient for oxygen when the following equation is balanced? Okay, that's worth an effort. So we're starting with an unbalanced equation that is NH3 and then O2. I'm going to leave some space here for coefficient. And then, let's see, who was that? I think that was the and then we get NO2 and water. So leave a little space there. And leave a little space here. Is that a gas? Yep, it's a gas. Okay. Budget method. What do we have in here? We don't have any polyatomics. And so we don't use that group trick. We do have one element, so that one saves till last. We got nitrogen, hydrogen, oxygen. So we do our initial tally, 1, 3, and 2, and 1 hydrogens, 2 oxygens, 3. Okay. We're going to save oxygens till last. Nitrogen's already balanced temporarily. So we're going to concentrate on hydrogens. Hydrogen occurs in only one place there, only one place here. So when you have an odd and an even, and the elements only occur in one place, cross multiply works the best. I think that was one trick that we didn't cover in class. So if I put a 2 over here and a 3 over here, that'll give us 6 hydrogens and 6 hydrogens. But now we have 2 nitrogens and 3 plus 2 is 5 oxygens. So we need 2 nitrogens here. That adds 4 plus 3 is 7. Okay, oops, 2. Okay, so now we got oxygen left. We need 7 oxygens out of this side. How do you get 7 from an even number? Use a fraction. Right, 7 halves of O2 will give you 7 oxygen atoms. Okay, so that's balanced, but it's not whole numbers. So we're going to get rid of the fraction. Multiply the whole thing through by 2. That's a 7. And this is 4. And this is 6. So what was the question? Coefficient for oxygen, 7. Okay. So I used single element trick, cross multiply trick, and fraction trick, all in the same problem. All right. Some of the coefficients for the following. Smallest total number. Okay. This one might be a real brain teaser. I think this one is a brain teaser. Does it show multiple steps to get there on that number 40? Not too many? Number 40? Oh, I thought you. Maybe it's tamer. Do we need to do it? Or you just need to practice? Yeah, practice more and more. All right. In the interest of time, we're going to skip 40. What's the equation? Is balanced with small set. We're going to skip that one too. Reaction occurs between sodium carbonate. Okay, here's one where you have to be able to convert the words, the names, into the formulas before you can do anything with it. Right? A reaction occurs between sodium carbonate. Sodium carbonate. Carbonate is a polyatomic with 2 minus. Sodium has 1 plus, so we need 2 there. Sodium carbonate and hydrochloric acid, HCl. To produce what? Sodium chloride and carbon dioxide and water. Okay. So that's what you need to know in order to balance the equation. And then you can go through with the budget method. Let's see, what is 45? A chemical reaction has the equation 2A plus B yields C. Which of the following figures best illustrates the stoichiometric ratio? All right, stoichiometric ratio refers to the reactants. So you can ignore anything that has C in it, doesn't belong there. Right? So Roman numeral 4 is out. That's not a stoichiometric ratio. You need 2 A's for every B. So if we count the first one, 1, 2, 3, 4, 5, 6, 7, 8, and 4, that's 2 to 1. One's good. The next one is 2, 4, 6, 8, 2, 4, 6. That's wrong. That's 1 to 1. And then Roman numeral 3 is flipped the other way. It's 2 to 1 in the wrong direction. Okay, so Roman numeral 1 is the only one that gives you the stoichiometric ratio of reactants A to B. All right, 46. What is it? 46 is out. So many grams of potassium chlorate decomposed according to the following equation. How many moles of oxygen are formed? All right, we should be able to get this one quick. That looks like it's balanced. Potassium chlorate. We used to use this one as mischievous chemistry students. Make a solution of potassium chlorate, fairly concentrated one, and then go drip it on the floor and let it dry. Once it's dried down to the solid, all it takes is an initiation, pressure, heat, whatever, and it'll decompose and produce oxygen, which makes a pop. So you do that in the lab before the professor has. It's better if only the lab tech is involved. Professors don't like it. So the lab tech come along and step on a dirty spot and it'll blow up under their foot. You hear this big pop and everybody has a hoorah. 7.11 grams. 7.11 grams. Remember, you can't go anywhere in this equation unless it's moles. All right, so if we're going to find moles of oxygen, then we need to convert this to moles first. So we need potassium, which is 3910, rounded off. Chlorine, 35, 45, and 3 oxygens is 48. 5, 13, 2, 6, 6, 12, 122.55. Divided into 7.11. Oops. That's better. So this is 5.80 times 10 to the minus 2 moles of potassium chloride. We want to convert that to moles of oxygen. Right? So we have potassium chlorate here, oxygen there. What's the ratio? Coefficients tell you the conversion factor. 3 here, 2 there. So I get 8.70 times 10 to the minus 2 moles of oxygen. Oh, it's in standard notation. Move 2 to the left. 0.087. There you go. How many grams of calcium nitrate can be produced by reacting excess? All right. If you've got one of the reactants is excess, then you just take what you're given for the other one and go all the way to the completion. Right? As long as you've got excess. You only have to do limiting reactants if you're given exact amounts of each of the reactants. Find out which one runs out first. For this reaction, what mass of P4O must be consumed if molecules of hydrogen are also consumed? All right. For 52, all you need to do is convert that oxygen into moles. And then use your coefficients to find out how much of the P2O5 carbon. All right. And once you find the moles of, moles of water, P4O10, convert that to moles. Then you find out how many moles of water, then you convert that to grams. Okay. Putting this equation. All right, for this one, what's the percent yield? Oh, this one's pretty quick. It looks complicated, but it's really not. 5.95 gram sample of silver nitrate is reacted with the barium chloride according to this equation to give 3.17 grams of silver chloride. So the actual is 3.17 grams of silver chloride. The theoretical you calculate from the stoichiometry. All right, so 5.95 grams of silver nitrate, 5.95 grams of silver nitrate is how many moles? All right, silver is 107.87. Nitrogen is 14.01 and 48 for the oxygens because there are 3 of them. Okay, 169.88 divided into 5.95 is 3.50 times 10 to the minus 2 moles of silver nitrate. And that equation looks like it's balanced. So if we want to find out silver chloride, what's the ratio of silver nitrate to silver chloride? It's 2 to 2 or 1 to 1. So this is also silver chloride, that many moles of silver chloride. So if we convert that to grams, we need the molar mass of silver chloride, which is, this is silver. Chloride is 35.45. Add those together. 7. So that's 143.32. And that's times this value, which is equal to 5.02 grams. So that's actually what you get out of it. I mean, that's theoretical. Theoretical. So we want to calculate the percent efficiency. 3.17 grams divided by 5.02 grams times 100. And that should be 63.1%. Okay. It was longer than I thought it would be. Let's see. What mass of carbon tetrachloride will be formed if 1.2 moles of methane react with 1.11 moles chlorine? This one has methane and chlorine given to you. You've got to decide which one is limiting before you can calculate the outcome. So if you have 1.20 moles of methane, let's see, 59. If you have 1.20 moles of methane, and you also combine it with 1.1 mole, 1.11 mole of chlorine, then what you do is say, convert all of this to carbon tetrachloride, right? And the ratio is the coefficients. they're 1 to 1. So this should give you 1.20 moles of carbon tetrachloride if it's all used up. What if we use this one? And carbon tetrachloride. What's the ratio there? It's 4 to 1. So I think it's fair to say this one's going to be the limiting one, right? It's going to be the smaller value. This is limiting. Well, we're going to have to calculate it anyway. So that's 0.28 moles of carbon tetrachloride. And it asks for grams. So now we have to convert this to grams. We just need carbon tetrachloride, which is 35.45 times 4 is 141.8 plus 12.01. So the molar mass is 153.81 times 0.28. And I get about 42.7 grams. D. My goodness, we're still in chapter 3. Which of the following statements is always true concerning a reaction represented by the following? To work this one, since it's approaching this reaction from different angles. Sometimes it compares mass, sometimes it compares moles. The best way to work this one is to look at the mole ratio as one part of the problem and the mass ratio as the other. So if you say, if you have work from stoichiometry, right? 2 ethane plus 7 oxygen, right? That's what we're working from. So the stoichiometry here is simply 2 moles per 7 moles is stoichiometric. Okay, so what would mass be stoichiometry wise? Right, it would be molar mass here, which is 24.02 for that, and 6.06 for this would be 8030, but we got 2 moles of it, so it'd be 60.08 grams would be that part of the molecule, part of the equation. And this is 32 times 7, which is 224. 14, 120, yeah, 224 grams. So this is the stoichiometric mass ratio. This is the mole ratio. This is the mass ratio at stoichiometric equivalent. Okay, so now if we look at the questions, A through E, I think. A says if we have equal masses, there is no limiting reactant. No, if we have equal masses, one of them is going to run out, right? Because that's not the stoichiometry. So A's out. If we have an equal number of moles, there's no limiting. That's not right either, because 2 to 7 is the ratio for stoichiometry. Okay. If we have more mass of C2H6 than O2, more mass of C2H6. If we have more mass, say we have more mass of this than that, then that would put us, oxygen is limiting. And that's true. C is true. None of these statements is true. All right, we can stop. We found the true one. My goodness. Are we ever gonna get out of chapter 3?
think it has 70 something,
Oh,
and then chapter 4 has 70 something as well.
really?
Yeah.
Oh, total,
Total.
but I didn't pick those. I didn't pick all of them. Okay. Do you guys want to stick around or you want me to just
Are you
post it?
Post it.
Yeah, I'll post it.
Yeah.
I'll tell you what, I'm gonna finish chapter 3 here.
Okay.
And then I'll splice in chapter 4 from a previous video
Okay.
and then post it.
It's the same question.
Same questions. So I'll keep going until I get done with chapter 3 and then I'll stop. So in that case, I better do it. Oh, I didn't put a number on that. That's 61. Okay. Now we're going to 62. Equal masses, 62. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Okay, hydrogen plus oxygen. This is where you have to know they're diatomic to form water. So if we're going to balance these, we need 2 of those. That means 4 hydrogens. So there's our balanced equation. Stoichiometry is 2 moles of hydrogen and 1 mole of oxygen. But the masses, that's what they're after, equal masses. So the mass of this would be to 4.04 grams, right? Because there are 4 hydrogens. And this would be 32 grams. So that's the mass stoichiometry. All right, if we have equal masses of hydrogen and oxygen, which substance is limiting? Equal masses? Well, take your pick. If we have 32 here and 32 there, then this is going to be excess and oxygen runs out. So oxygen is limiting. 64. Thanks for sticking for a half hour anyway. Yeah, all right. Let's see, 64. For the reaction, nitrogen plus hydrogen yields dinitrogen tetrahydride. If the percent yield for this reaction is 82, what's the actual mass? Okay. Hydrazine, I should have said hydrazine. That's a special name. Nitrogen plus hydrogen, correct? 2 hydrogens. And hydrazine. Okay. That's what the Nazis used in their rocket plane and killed a bunch of the workers doing it. If the percent yield is 82%, 82% yield, that means if we have 100 grams theoretical here, we actually only get 82% or 82 grams. Actual mass produced when 25.57 grams, 25.57 grams, and 4.45 grams, 4.45 grams. Okay, so since we're given both masses, we've got to find out which one's limiting. So we have to convert each one to moles, right? This is going to be times, right? Numerator, denominator. So dinitrogen would be 2802. And that'll give us the number of moles. 25.57 divided by 28.02, which is 0.9126 moles of nitrogen. And hydrogen is going to be 2.02 grams per mole. So 4.45 divided by 2.02 is 2.203 moles of hydrogen. Oops, not water, hydrogen. Okay. We could do it the other way, the way that we've been doing it, say, if all of this is used up and all that's used up. They're too close, right? The ratio is 1 to 2, and this is almost 1 to 2. So I think we're gonna have to do it the old-fashioned way. So 1 to 1 here means that we would produce here the exact same amount moles of hydrazine. And this was 2 to 1, so we divide this by 2. And that's 1.102 moles. Okay. Nitrogen's the limiting reactant. This is the amount of hydrazine that's actually produced. And we need to convert that back to grams. So we need the molar mass of hydrazine. 2 times 1401 is 28.02. And then 4.04 for hydrogens, 3206. And this gives us the theoretical amount of hydrazine. 32.06. And let's see, let me do this. There we go. 6 times. So this equals 29.3 grams. Theoretical. We want the actual amount. We know the yield is that. So what does that mean? Well, remember the formula. Actual divided by theoretical times 100. In this case, it's equal to 82%. So if we know the theoretical is 29.3 divided by the actual times 100 equals 82, then all we have to do is solve for the actual. Right? So actual equal, 82.0%. This is in the numerator here, it goes into the denominator on this side. This is in the denominator, it goes into the numerator. Right, and then we solve. Uh, 24.0 rounded off grams of hydrazine. 24 grams. Yeah, 24 grams. Molar mass of tetraphosphorus decaoxide. You just need to know how to write the formula. Right? That's a type 3 compound because it says how many of each one. So just, oh, are you done with that? You still writing? Okay. Uh, 66. Tetraphosphorus decaoxide. That would be your formula. And then you just calculate the molar mass. And it should be 284. Right? 10 times 16 and 4 times 30.97. Let's see, 69. Which of the following contains the greatest number of moles of carbon atoms? All right, this is one where you would set it up as an assembly line, like Henry Ford. All contain the same number, right? So, 58 grams C4H10, C4H10, 58 grams. 46, oops, be consistent here. C2H5OH, C2H5OH, and that's 46 grams. And carbon dioxide, 44 grams. And glucose is 180 grams. All right. I got a sneaking suspicion. What's the molar mass here? I bet I know what's happening. That's 58 gram sample. 4 times 12.01, right, for carbon. And then 10.10 for hydrogen, because 1.01 times 10 is 58.14 grams. Grams per mole. I thought so. So this is 2 carbons, 24.02, 6 hydrogens, and 1 oxygen, 3608. Ooh, okay, I missed my guess. Grams per mole. Carbon dioxide is 4401. Maybe I calculated that wrong. Let's see, 12.01 times 2, and then 6.06 for the hydrogens, and then 16 for the oxygens. I did make that one wrong, 46. My first assumption was correct. These masses are all the molar masses for these compounds. 12.01 times 6, and then 12.12 for hydrogens, and then 6 times 16. 180.1. 180.1 grams per mole. Okay, so what we're saying is each one of these is 1 mole of the compound. So if you've got 1 mole of each one of these, and the greatest number of moles of carbon atoms, you just compare the formulas, because we've got 1 mole of each one. So this one has 6 moles, which is the most. Okay. That one right there. This is 1 mole of each one, so that one wins. 70. Let's see, an unknown molecule is found to consist 24.2% carbon, 4% hydrogen. The remaining is chlorine. What's the molecular formula of the molecule, given that the molecular mass is found to be approximately 150? I think you guys can do this one. In order to find out what percent composition is chlorine, you just take 4 plus 24.2 and subtract it from 100. That's your chlorine. And then you say you got a 100 gram sample, turn those into grams, and you're off to the races. Naturally occurring iron contains percentages of those 4 isotopes. The respective atomic masses are, so here they actually give you the atomic masses. We don't have to assume anything. Calculate the average atomic mass. So you know how to do that. Turn the percent into a fraction. So 5.82%, 71. 5.82% is 0.0582. Then multiply that times, let's see, 53.94. That gives you a value. Do the same thing for all four of them, then add them together, and Bob's your uncle. I think that's what they say in England. Let's see. Oh, okay, 73. This one, not all students, but some get confused with this one. Give the empirical formula for the following compounds. The definition of the empirical formula is the simplest whole number ratio of atoms in a molecule. So count them up, right? That first one, we have 6 carbons and 6 hydrogens, right? The simplest ratio is 1 to 1. 6 to 6 is 1 to 1. So it's CH. That's the empirical formula. The next one is 2 carbons and 4 hydrogens, which reduces to 1 and 2. The third one takes a little counting, right? Carbon, hydrogen, oxygen. So carbons are 1, 2, 3, 4, 5, 6. Oxygens are also 6. Hydrogens are 12. So C6H12O6 reduces to the simplest number of 1 to 2 to 1. That's the empirical formula. Oh, the last one. Let's see. So carbons, you got 1, 2, 3, 4, 5, 6. Let me put this on the board. C6, this is the molecular formula. H what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H 10 and O 2. Okay. We can divide that all through by a 2. So now it's C3H5O. This would be the empirical formula. Remember, if we were working backwards to go this direction, we'd be looking for the multiplier. And the multiplier in this case would be 2. All right. So an unknown substance dissolves readily in water, but not in benzene, which is a nonpolar solvent. Molecules of what type are present in the substance? All right. If it dissolves in water, water is polar. Benzene, which is C6H6, is nonpolar. This is polar. You just need your rule of thumb. Like dissolves like. If the substance dissolves in water, it must be polar. Right? That's why B is the answer. It has to be polar. Okay. Number 5. Which of the following is not a strong base? All right. Strong bases are composed of alkaline metal hydroxides and alkaline earth hydroxides. That's A, B, D, and E. Ammonia is not any of those. Ammonia then is a weak base. Okay, about 6. Which of the following is paired incorrectly? All right. A, sulfuric acid is a strong acid. B, nitric acid is a strong acid. That's wrong. There you found your answer. Barium hydroxide is a strong base, hydrochloric acid is a strong acid, and ammonia is a weak base. So we found our answer. The incorrectly paired is B. Excuse me. We didn't talk about this one in class. Number 7. B. Number 7, the man who discovered the essential nature of acids through solution conductivity studies is Arrhenius. That would have been in your textbook in chapter 4. We didn't discuss that in class, so that just drives home the point. You need to read your textbook. Number 9. .4 gram sample of HF is dissolved in water to give 2 times 10 to the second milliliters. That's 200 milliliters. The concentration of the solution is what? Well, all the concentrations are in molarity. Molarity equals moles divided by volume, and volume has to be in liters. Right? So how many moles do we have? It's not given. We have to calculate it. 16.4 grams. So what's the molar mass of HF? Well, it's 1.01 and 19 for fluorine. So that's 2001. That'll give you the number of moles. It's 0.820 moles. So 0.820. And then how many liters is 200 milliliters? 3 places to the left is 0.2 liters. So I did that wrong. Let's do that again. There we go. 4.1 molar. That's D. Let's see. What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? Right. In this case, we're using the same formula. And that's 14. But we're solving it for a different variable. What mass of calcium chloride? Well, there's no mass in that formula. But if we find the number of moles, no problem, because we have the formula for calcium chloride. So we're actually solving it for moles. Moles equals molarity times volume. So the molarity is 1.49 molar and 3.95 liters. Okay, that'll give us the number of moles. Which is 5.89. Now we can convert moles to mass. So what's the molar mass of calcium chloride? Well, calcium, I think, is 40. 40.08. And chloride, we have 2 of them. 2 times 35.45. Okay. 40.08 and 35.45 times 2, add that is 110.98. 110.98 times 5.89 is 65.3. Which is, oh, excuse me. Oh, wrong decimal place. One more move. See, that didn't make any sense. 6 times 100 is 600. So I should have seen that one coming. So that's E. (16) What mass of solute is contained in 256 milliliters of 0.838 molar ammonium chloride? All right. I shouldn't have to work this one out completely. What mass of solute? The mass we can't get from the formula. We have to get moles first. So, if we use this formula and we solve for moles, then I'll set it up for you. 0.838. And volume has to be in liters when the formula is in this format. 0.256 liters. That will give you moles. Then you need molar mass of ammonium chloride, right? In which case you need to know how to write ammonium chloride to get the molar mass. I think that's the real test of number 16. You have to be able to write ammonium chloride, otherwise you're stuck. You can't find you should come up with 11.5 grams. (17) 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.450 liters of solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? All right. This is, we have to calculate the concentration of the barium hydroxide to begin with. That's the concentrated version. And then we're going to dilute it. So it's a multi-step problem. And I will work this one out for you. 74.28 gram sample of barium hydroxide. 74.28 grams. We want to convert to moles. So we need barium hydroxide. Barium is a monster atom. 137.33. And hydroxide, we got 2 oxygens, 32, and 2 hydrogens, 2.02. So that's 5, 3, 4, 11, 6, 7, 171.35. Divided into 74.28. Is, 0.433. 0.433 moles. Okay, so now we can calculate the concentration of barium hydroxide, the concentrated version, the concentrated molarity, which is that many grams in 2.450. So this is going to be 0.433 moles per 2.450 liters. Which is 0.177 molar. Okay? So remember, molarity of the concentrated, volume concentrated equals molarity of the dilute times the volume of the dilute. So the question is, how many milliliters of the solution must be diluted? How many milliliters of the concentrated solution must be diluted? So we're solving for this one. So we want 0.1 molar and 1 liter from 0.177. And this volume is going to be in liters. So then we'd have to convert it to milliliters to find the answer. So 0.1 and 0.177 divide, and then 1,000 times 565. Yeah, 565 milliliters. Okay, that's A. All right, number 18. Let's see, what volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 0.145 molar? This is a dilution problem. So you need, the best way to do this one is to say molarity of the concentrated, volume of the concentrated, molarity of the dilute, volume of the dilute. What volume of the concentrated? That's the unknown. This one's 18 molar. We want to end up with 0.145 molar, and a total volume of, let's see, the answer's in milliliters. Let's make the volume milliliters. So what's 2.3 liters? 3 places to the right is 2,300 milliliters. Then you set up your problem, just like we did before. Solve for that one. And you should end up with 19 milliliters of concentrated sulfuric acid diluted to 2.3 liters. All right. So now we're going to classify reactions. 28. So, for these two reactions, what do we have? What are our options? Oxidation reduction, redox. B is acid base, and C is precipitation. Okay. So what do we got up there? Do we have precipitation reactions? Yeah, we got 2 solutions on the left and precipitation on the right. 2 solutions on the left, for both of them. We have precipitates. So this one is definitely an answer. Do we have oxidation reduction? Well, in order to be absolutely certain about that one, we'd have to do the oxidation states for each of the elements. So you need to know your rules. For the zinc bromide, for instance, we have to assume that bromine is -1. It's a halogen. Otherwise, we can't do the other one. This one's +2. Well, did the zinc change? Well, zinc nitrate, right? This one's a -1. This one's a +2. Zinc didn't change. And we look at silver nitrate. Silver is +1 and +1 on both sides. It didn't change. So the first one is not an oxidation reduction reaction. And that's the only one we need to do, because we know that the first one's not redox. That means that they both can't be redox. So A is not a valid description, because we know that one of them is not. Acid base. Neither one of those reactions has an acid in it or a base in it. So we know that the only one that works is C, precipitation reactions. How about the next one? All of the following reactions can be classified as. So if we find one that's not, then we can't say all of them. So all of them, rule of thumb, 29. We have redox, combustion, precipitation. A is redox, B is precipitation, and C is combustion. Right? Oh, I got them backwards. Sorry. Combustion and precipitation. Okay. Let's look at them. What's the rule of thumb for redox? If you can find it, element on one side is in a compound on the other side. Is that true for each one? The first one, yes. Aluminum is in a compound on the right, its element on the left. Silver for the second one is on the right, and silver in compound is on the left. That's a redox. Combustion reactions are always redox. Plus, oxygen is an element on the left and it's in a compound on the right. So all of them are redox. Now, how about combustion? You have to have oxygen, elemental oxygen, in order to have combustion. It has to be a reactant. So we've only got one of them in there. So that means B doesn't work. How about precipitation? Well, in order to have precipitation, you need two solutions put together to give you, and it's a double replacement, to give you a precipitate. And none of them have that. Right? Even though they form a solid, they don't meet the criteria for a combination of solutions to make a precipitation. Right? So the only one that works is A. They're all oxidation reductions. Which of the following salts is insoluble in water? That's 32. You need your chart in useful information and look up combinations of cations and anions and see which one precipitates. As it turns out, all of them are soluble in water. Each one of those. Just look them up. You'll find that all the squares are clear. And of course, if you know the rules, you know that all alkali metals are soluble, make soluble salts. All nitrates are soluble, and most chlorides are soluble, with a handful of exceptions. So calcium chloride is soluble. So your answer there is E. All of them are soluble. How about 37? Consider an aqueous solution of calcium nitrate added to a solution of sodium phosphate. What's the formula of the solid formed in the reaction? Okay, calcium nitrate, right? Calcium nitrate. That's a -1. This is a 2+, so we need two of these. And that solution is added to sodium phosphate. Sodium phosphate. That's a polyatomic ion with a 3-, and this is a +1, so we need 3 there. Okay? Now, if these are aqueous solutions, that means we have calcium plus 2 nitrates plus 3 sodiums plus 1 phosphate. Okay? So now this combined with that is what? It's soluble. Sodium nitrate soluble. Calcium phosphate, we look it up on our chart, calcium phosphate is insoluble. So that means we're going to combine calcium with phosphate, which means we need 3 here and 2 there. Cross multiply. So Ca3PO4 taken 2 times is C. That is your answer. That's the precipitate. All right. For this one, let's see, 38 through 40. Do I have time to do that one? 45, 50, 52. Okay, I'm going to have to be quick with this one. Here we go. 38, 39, and 40 are based upon the reaction of barium chloride and silver nitrate. The balanced molecular equation contains which of the following? All right, let's do that one because you need to know how to write each one of these equations. And 38, 39, and 40. First of all, you have to write the compounds. Barium chloride. That's a 2. is combined with silver nitrate. Silver combines with chlorine. To make a solid. And barium nitrate is soluble. And this needs to be 2. Okay. Now let's balance it. 1 barium, 2 chlorines, 2 silvers, 2 nitrates. That's balanced. Once you've got the equation balanced, then you can answer 38. Which one of these is contained in that reaction? And take the coefficients into account and the phases. Silver chloride solid, 2. So that's B for 38. The others don't match up. 39 requires you to write the complete ionic equation. So barium, 2 plus 2 chlorines, plus 2 silvers, plus 2 nitrates, yields 2 silver chlorides, plus a barium, plus 2 nitrates. Okay, once you got the balanced molecular equation, you just split out your ions and take the coefficients, take the subscripts into the coefficients. So 2 here means 2 there. All right, so which one of these is correct? 2 silvers right here. So that's C. For the net ionic equation, we just cancel the spectators. So we got silver and chlorine make the solid, so we have to keep them. But barium is on both sides, and nitrate is on both sides. So now we have this one, this one, this one. But notice they can be reduced further. 2, 2, and 2 means 1, 1, and 1. So if we do that, that, and that, now we have 1 silver, 1 chloride yields 1 silver chloride. So which one of these is in there? 1 silver. That one. So that would be A. That's how you answer this question. And you have to know lots of things. You have to know how to write the compounds. You have to know how to put them in the chemical equation. You have to know how to balance the equation. Then you have to know how to split them out into their ions. All right. $45. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? Well, all you have to do is say strontium chloride, which is 2, and that is added to sodium sulfate, like that, aqueous. You do a double replacement. You say sodium and chloride. What does that make? That makes a soluble compound. Those are spectators. Strontium sulfate is a solid. So the strontium and the sulfate have to be kept. Sodium and chloride are spectators. So, which we have sodium ion and chloride ion. Two of these, chloride and sodium, those are both spectators. Let's see, I'm coming up on 3:45, is it? Oh, I got till 3:50. Okay. I got 12 minutes. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar sulfuric acid? All right. This is an acid-base reaction. And probably the most efficient way to work this one is to write the acid-base equation, which is sodium hydroxide plus sulfuric acid makes what? It makes the salt, sodium sulfate, and water. So how do we balance that? We need 2 sodiums and we need 2 waters. So this tells us the ratio of sodium hydroxide to sulfuric acid. If we know 25 milliliters of 2.7 molar sulfuric acid, remember, moles equals molarity times volume. So if we say 25 milliliters times 2.7 molar, then what are we going to get? We're not going to get moles, we're going to get millimoles. .5 millimoles. Okay. What's the mass of sodium hydroxide that will react with that? Well, the ratio is for every one of these, you need 2 of those. So times 2 equals the millimoles of sodium hydroxide. 135. Okay. Now here's where we have to go back to moles, because in order to get mass out of this, we need moles. So 135 millimoles is 135 times 10 to the minus 3 moles of sodium hydroxide. So now we need moles, molar mass of sodium hydroxide. All right, so sodium is 23, 23. Oxygen is 16, and hydrogen is 1.01, which is 40.01. Times, let's see, let's do that. And divide by 1,000. And then multiply. 5.4 grams. C is your answer. Now, if these problems seem difficult, all I can say is you haven't worked enough of them. If you're not working these problems in the review document, then you're going to be lost. .52, in which of the following does nitrogen have an oxidation state of +4? All right. Let's see. I think we got time to do this. A, B, C, D, and E. Yep. Sodium nitrite, ammonium chloride, dinitrogen monoxide, which is laughing gas, nitrogen dioxide, and NO3. We're looking for +4 oxidation state for nitrogen. Right? If this is -2, and this is a +1, then that's a -6. -6 and a +1 equals a -5. So this has to be a +5. That's not it. -2 is a -4 + 4. There it is right there. It's B. Now you can do the rest of them, if you have time, if you want to, but we found our answer. All right, 53. The oxidation state of iodine in IO3 minus. What's missing? The cation. IO3 minus is an anion, and we don't like unbalanced charges. But we left the cation out because it won't matter. Because the IO3 minus tells us that the summation of oxidation states must be equal to -1. So if we've got -2 for oxygen times 3 is -6, and we need one of them to be minus, we only have to balance a -5. So that's +5. Check yourself. -6 and a +5 is a -1. So D is your answer. '55. Which of the following statements is not true? All right. A through E. Let's see. A. When a metal reacts with a nonmetal, an ionic compound is formed. True. B. A metal-nonmetal reaction can always be assumed to be an oxidation-reduction reaction. Yes, because you have elements on the reactant side and a compound on the product side. C. Two nonmetals can undergo an oxidation-reduction reaction. Oh yeah. All they have to do is change their oxidation states. And we've calculated some of those. That's true. D. When two nonmetals react, the compound formed is ionic. Nope. Two nonmetals react, it's always covalent. They have to share electrons. And E, a metal-nonmetal reaction involves electron transfer. That's true. That's a redox reaction. So D is the only one that's wrong. Let's see. Coming down to the wire. In this reaction, calcium plus oxygen yields calcium oxide. Which species is oxidized? All right. 2 calciums plus an oxygen yields 2 calcium oxide. Okay, gas, solid. Okay. These are both 0 because they're elements. This one's a -2, this one's a +2. So, which one's oxidized? Oxidation is loss. Which one lost electrons? Well, if we go from a 0 to a 2+, that means it had to lose 2 electrons. So that's it. That's the oxidation. Calcium, the calcium metal, C, is the one that was oxidized. Let's see. Oh, we got a different one here. 57. In this reaction, chlorine is what? Okay. Cesium plus chlorine yields cesium chloride. Okay. So let's identify what happens here. This one is -1, this is +1. Is that right? Yeah. Cesium is an alkali metal. It's always +1. Okay, so if we go from here to here, That's a loss of 1 electron per cesium. This is oxidation. That means this one must be a gain of 1 electron per chlorine, which is a reduction. Okay, that means if this is oxidized, this must be the reducing agent. And this must be the oxidizing agent. Okay, so the reducing, let's see, chlorine. Chlorine is the oxidizing agent, B. All right, but it can't be the oxidizing and reducing. Chlorine, is it oxidized? No, it's reduced. Is it the electron donor? No, because it gains electrons, right? So the only answer in that set is B. It's an oxidizing agent, and that's the only possible answer that's given. All right. Which of the following statements are true? Oxidation and reduction. Let's see. A, cannot occur independently of each other. That's true. They have to occur together. B, accompany all chemical reactions. No, not always. C, describe the loss and gain of electrons respectively. Oxidation is loss, reduction is gain. True. A and C are true. How about D? Result in a change in the oxidation states of the species? Yes. A, C, and D are all true. B is false. 63. We might run over a minute or two. Balance the following oxidation reduction reaction using the oxidation number method. In the balanced equation, the coefficient of Br minus. Okay, this should be fairly quick. Fe plus Br2 yields Fe3 plus Br minus. Okay, 0, 0, 3 plus, and minus 1. So this one is a loss of 3 electrons per iron. This one is a gain of 1 electron per bromine. Okay, so we need 3 electrons down here. But how do you put a coefficient in there to give you 3? If I put a 2 here, that's 4, right? Because if I put a 2 there, that's only 2 electrons. So what we have to do is actually cross multiply. In other words, we've got to settle on a value of 6 electrons. Okay, which means this is times 2, 2, and 2, and this is times, well, we need 6. So we need 6 here, and we need 3 there, times 6. Okay, so 2, let's see if it, 2 iron, 6 bromine, 6 bromine. That's correct. Yep, and it gives us the right balance of electrons, too. So the oxidation number, coefficient of Br minus is 6, right there. We got more. Okay, hopefully this won't take too long because I'm out of time. 66. Okay, select the spectator ions for the following reaction. All right, the spectator ions, the best way to do that is to identify the solid. Lead 2 chloride is a solid. You can look that up in your table. That means potassium and nitrates are all soluble. So potassium +1 and nitrate -1 are spectators. There they are right there. 68. Identify the precipitate formed, if any, in the following reaction. So you just trade cations. So iron and carbonate. Is that a precipitate? Well, it depends. What's Fe nitrate? It's 2, Fe2. Fe2 plus. And carbonate is 2 minus. So FeCO3 is a solid. Right? So B would be a correct answer. Ammonia and nitrate is soluble. Right? So that doesn't work. We just had to get the formula for iron and carbonate correctly written. Following, does nitrogen have the highest oxidation state? In which one? All right, you have to go through and determine the oxidation numbers and compare them. Should come out with nitric acid. 71, in which of the following does iodine have the lowest oxidation state? Well, same thing. You have to determine what is the oxidation state of iodine in each one of these and compare them. And you should come out with D. That would be I minus 1. That's the lowest oxidation state. In other words, the more negative it is, the lower it is. So if you've got some positives in there, then you'll have some high positives, mid, low positives. Once you get into the negatives, I2 is 0, but I minus 1 for D is the lowest oxidation state. And hopefully that's all the ones I had planned. Yes.